Good morning, good afternoon, and good evening, ladies and gentlemen. This is Glenn Tan speaking. This time, I'm going to talk about GNV6 internal equipments.
This presentation divides into these four parts. We also take a video of GNV6 outdoor unit internal equipments, which can help you to recognize them. If you are interested, you can scan this QR code or go to the linkage to watch this video. Next chapter, we will go to the heat exchanger and pressure vessel. Subcooler located here just after the IPN cooler and the outdoor heat exchanger, and here is the appearance. From this working graph, you can find that this is the prey on the left side and right side. They are just two different flow, and we just make them to make heat exchange inside. From this sectional view, you can find that this is actually the inside prey. It is not flat. We make it to be uneven to higher the heat transfer efficiency. The purpose is just to ensure the refrigerant to become completely gas. So in cooling, we can higher the subcooling degree, which include this part. And in heating, we can ensure, as we would like to adopt the EVI, which is to inject the vapor or the gas to the compressor here inside it, and which means at this outlet it should be 100% vapor or gas. How we can achieve it is use this subcooler. The refrigerant will first get expanded to become low pressure and temperature, then it can absorb heat from the main row. Then itself will become the gas or the vapor, then into the EVI. About the heat exchanger, compared with GNV5, GNV6 improve or upgrade lots of the points. First is the partition heat exchanger design. For the GNV5, this is the outdoor heat exchanger. You can find that this is the outdoor distributor, and for this whole outdoor heat exchanger, it is just one. And for GNV6, we divide it into these two partitions. And the benefit, just compared with GNV5, it is that this is the distributor when you need to distribute the liquid refrigerant in heating from here to the furthest passes. This is actually the small size tube, and for mass production, it is not that easy to control this lens. And the result it is that if we cannot ensure this lens, we will make the distribution not that even. And not that even also in heating, that means it can be loss of the ice easily on the surface of the outdoor heat exchanger, and which means for the heating, which is the performance, it will be poor. And for GNV6, also we adopt the distributor to distribute the liquid refrigerant, but as we divide it into two, so from the distributor to the furthest pass, the length is only half of it. So it will make the control in mass production more easier. And the next is from the distributor to the outdoor heat exchanger. For GNV5, the flow is only one, and it become only one. And for GNV6, we adopt this from here, it is one, and then divide into two, and then here we combine these two together and make it to be one. So from this design, we can higher the heat transfer efficiency and also amount, either from the simulation or from the text results. And next is for the fin features. And for GNV5 is slip fin. you can find on the surface, we just make lots of the slip on the surface. And for GMV6, we just make the flag to be uneven. And from the heat transfer efficiency, definitely GMV5 is higher. However, in heating mode, as the outdoor heat exchanger, there are will generate the condensing water. In low temperature situation, it will become ice, which means the ice will stick on the surface of the fin. And if there are lots of the slip here, when we do the defrost, which will make the ice to become water, and the water will not flow out easily because they will just stick on this slip. And then next time when it is going back to heating, this will cool down again and become ice easily, which means for heating performance, slip fin is not that good. And for this corrugated fin, as there is no slip on the surface, and the water which is become from the ice can flow out easily, which we can higher the heating performance, especially in low temperature heating, and also make it to be easier defrosting. IPN cooler located here. Because we apply the inverter compressor, and lots of the heat will generate from the compressor IPN, and we apply the refrigerant to cool it down. So just compare with the air cool, it is max 8 degrees, will be lower. And what we call is subcooling. It is because at this part it is completely liquid, either heating or cooling. Besides, the whole electric box, the surface of it is the aluminum alloy. The purpose of it is just to release more heat. And also you can find at the surface there are lots of the lips. This also to help to release the heat. It will be 4 times higher than the thermal, than the metal plate, which is the GMV5. And for the IPN cooler, you may have a worry that on the surface of it, if in a high humidity condition, we will be condensing water, and the condensed water, if it generates at the IPN, it will also very easy to make it to be damaged. And for this one, we already consider about it, and also we have the solution, which is to higher the temperature of this refrigerant to avoid the refrigerant lower than the dew point, which this will not generate the condensing water. Heat bypass antifreeze pipe. That means at the bottom of the outdoor heat exchanger, it is another cycle, which is not the same as the upper side. Also, as you can find that at the outdoor heat exchanger for the top discharge, at the bottom side, which is this part, the heat transfer efficiency is not that high because the air volume is not that high, as it is far away from the top fan, and the fan, if it is far away, and also the air volume not that high, also indicates the heat transfer efficiency also not that high. And for on the other hand, when during the defrosting, and the water which is become from the ice will always flow down at the bottom, and when it go back to heating, the bottom, it is the coldest one, and on this one it will make the water to become ice easily. So just consider of this part, we make it to be another cycle, which is to just like this, located here. And when we do the defrost, just like this, we send the hot gas to melt down the ice on the outdoor heat exchanger, and also a partial refrigerant, which is here, will conduct to the button, which is conduct to here to melt down or to prevent the water become ice. And this controlled by this gas bypass valve. On the other hand, it also has the gas bypass function, which can make the balance between the high and low pressure when we turn on this one. Gas liquid separator located here. Here is the appearance. You have two parts. From this sectional view, you can find that here is the inlet and here is the outlet. The function of this one is by gravity or centrifugal force will separate the liquid part, which is make the liquid part will accumulate it here, and only the gas which will flow up and from this tube get in it, and from here to get outside, which is into the compressor. And the function of it is just to prevent the compressor, the liquid hammer. And also you will find this one, a hole here, which actually it is this one. There are a filter at the surface. The purpose of this one is just make the oil to flow into this one to lubricate the compressor, not the liquid refrigerant. Oil separator located here, which is at the discharge of the compressor. The purpose of this one is just to separate the oil from the high pressure and temperature gas, and this can prevent the oil get into the system and also make the oil flow back to the compressor for lubrication. For GMV5 we have two oil separators, but for GMV6 there is only one, but we create another oil return passes, which is the oil which is separated from here, and then it will have two passes to flow back to the compressor and back to the oil separator, which is this one. Here is the appearance. The gas in here, and after separated, the gas will flow out from here. And this one is the oil. And here is how it will operate. And also the oil, which is from here, you have two passes. The first is the major oil return, which is this one is in at any condition, either cooling or heating, it will always turn on to conduct the oil flow back to the compressor. And the other one is the assistant oil return valve. The purpose of this one is in low temperature heating, when at that time the oil viscosity is very low because the low temperature, right? And on the other hand, at low temperature heating, always we require the compressor to be high frequency, and high frequency, that means the require more oil for lubrication. If only with this major oil return, that is not enough, so we just create another bypass, which is this one, to conduct more oil to flow back to the compressor for lubrication in low temperature heating to ensure the reliability. Compressor, which is located here. Here is the sectional view. First of all, this compressor is also from Hitachi, and it has the EVI, which is short for Enhanced Vapor Injection. This is very helpful in low temperature heating. And just walk here. In heating, a partial refrigerant will get through this subcooler EXV, and itself will become the low pressure and temperature. Then it can absorb heat from the main roll, which itself will become the gas. At that time, we flow out, and then we flow this pipe and flow to the this one, controlled by the EVI EXV, and then inject into the compressor. And here is a question that this subcooler valve during EVI, it is on or off. The question is, it should be off because we need to conduct the refrigerant, which is this part, to the compressor. If you make it to be on, as you can find that it connects to this part, which is the low pressure, and the refrigerant always will go to the low pressure, not the medium pressure, which is for the EVI injection. That's all for this part of the presentation. If you still have any other question, just feel free to contact me on my personal email address.